error propagation, how you can get a general formula that can be used to get the errors in addition and errors in the subtraction. Now we can develop a formula still which can be used to get absolute error, percentage errors, relative errors, absolute errors in multiplication. So let us look at the error propagation in the multiplication. More especially when you're multiplying the two terms. If you're having A as the exact value, approximated to small a with an error EA, and B is the exact value approximated to small b with an error, small error in b. Meaning that the exact value, get the approximated value a plus the error which was made in approximating that value. Then to get the true value of b, you get the approximated value of b plus the error which was committed in approximating that value b. So now we're looking at multiplication. We're multiplying two numbers. We're multiplying a times b. But it's still from the definition of the error equals to an exact value minus the inexact value. Exact value minus the inexact value. So when you get these two numbers, because of under multiplication and multiply them together, so the error here, the error will be the exact value of multiplying the two values a and b minus when you multiply the approximated values small a and small b. That is how you get the error which is committed in that function. Now, this one here, from this definition here, the a is the same as the inexact a plus the error in a, then times b, which is b, plus the error in b, then minus the ab. So the error here will open this bracket. When you open multiply a times b, you have ab, multiply a times the error in a, you have a, error in b again, then multiply error in a times b, you have b times the error in A, you have A, error in A, you have times the error in A, times error in B, then minus AB when you open that bracket. This term here and that term they are the same, they will vanish, then you remain with the error equals to AEB plus error a times the error in b plus b, error in a plus EA, EB. These are the two errors. Then you make an assumption that if the value of a is very small compared to the error in a, and that if the value of a, this one, is very if the error in a is very small compared to the value of a, that is what I want us to mean there. If the value, the error made in a is so small compared, small compared to the value of a, and the error committed in b is also very small, that is the meaning, very small compared to the value of b, then the product of the two errors A and error in B approximately goes to 0. Like if those errors, you're making an assumption, if the errors, like the error in A is 0.0000005 times 0.00008, that is their very small errors. When you multiply this one here and use your calculator, will give you that the product of those ones. So that is the meaning. That if those two values, these two errors are very small, compared to the A. This was also very small compared to B. Then when we multiply these two errors, you get approximately 0. So meaning that the error here will equal to the value of A, the error in B, plus the value of B times the error in A. Then we're interested in getting the absolute error. The absolute error, that is the absolute error is the maximum possible error. The moment they talk about the maximum possible error in the product, that is the absolute error. And this one here, we take the magnitude of A error in B plus B error in A. That is that. So if we separate, don't forget to use the triangle inequality principle. Triangular inequality principle here. So here this one here will be A error in B plus B error in A. And if A and B are positive numbers, you can pull out and say the absolute error will be A into error in B plus B into error in A. And this is how you get the absolute error in the products of the two numbers. We can stretch further and look at the relative error. The relative error. We can derive the general formula for the relative error when we are getting the product of the two numbers. We say the relative error is equal to the absolute error over the inexact value. And the inexact value, you say that is the working value. You get the product of those two numbers. This one here, this is the inexact value, the approximated values, the AB. So here, we'll have now the absolute error. We come to this step here, and we say now we are dividing A magnitude error in B, and we are dividing this whole term, we are dividing it with the AB plus we are getting this term here, which is B plus the error in A, and we are dividing it with the AB. We divide by the working value here, by the working value there. So here we made with the relative error. Here, this A will cancel with the A, then this B will cancel with the B. Then we make the relative error is equal to error in A over the value of A plus the error in B over the value of B. And that is the general statement. You can even quote it direct if you are having two numbers. If they have given you two values of X and Y, then they say what is the relative error in that expression. But quote that the error in X over X plus the error in Y over Y. You get it? The absolute error in the relative error. So if you can stretch further to get the percentage error, the percentage error, we say the percentage error is equal to relative error times 100%. So in the product there, if I get the percentage error, it will be now, we have our relative error, this one here, which will be error in A over A plus error in B over B. Everything is times 100%. Then you get the percentage error which is committed in the product. We can now look at the propagation of errors in the division. When we look at the division, how we can generate a general formula we can use to find errors in the division. We can use, if we want, we can use the if X, but change the variable, if X is the exact value, approximated to x with an error ex and capital Y with uppercase is the exact value approximated to small y with an error x ex. That is the absolute error in x. This is an error ey. So by definition, the exact value x will be the approximated value plus the maximum possible error in x. Then y will be the approximated value of y plus the maximum possible error in y. X plus the maximum possible error in x, y plus the approximated value of y plus the error in y. Still, we are using the same argument that the exact value, the error which is committed, is equal to the exact value minus the inexact value. Exact value minus the inexact value. So the error will give us, here we are dividing, is a quotient, we are dividing x over y. So the exact value will be x over y minus the approximated value, which is small x over small y. Small x over small y. So by definition here, this capital X, this one here, it will be the same as approximated x plus the error in x over y plus the approximated value plus the error in y. Then minus x over y. X over y. So at this stage here, this term here, we rationalize the denominator. And from the pure mathematics, when you are rationalizing, you multiply this term with here you change the sign. If this is a plus, you change the sign negative, so it will be x plus ex times y minus ey over y plus ey times y minus ey. And mathematically then minus this term which is x over y. And mathematically here, we have not done anything because this one here can cancel out. This one here we can cancel it out and remain in this one. That is rationalizing. This one here, the x plus y plus ey, y minus ey, this is the difference of two squares. So we already don't have to labor here opening this bracket, we already labor opening this bracket, but this is the difference of two squares here. And the whole thing there will become, we're opening this bracket, the error will equal to, we open this one here, will be xy, this one times this one, minus xey, then we come here, this one times this, which allow plus y, ex, then multiply this one and this one, which allow the ex and ey. And everything is over. This is the difference of two squares, so it will be y squared minus ey squared. Then minus x over y. Then we make an assumption, that if the error in x is also small compared to x, and the error in y is also very, very small compared to y, then the error in x times the error in y is approximately equal to 0, and the error in y squared, because this is the product of the error in y times the error. When you multiply an error if it is very small, multiply two small values, you also approximately get 0 there. We make those assumptions. You don't proceed before making those assumptions. So if we say that the product here will vanish, also that will be the denominator will vanish. So we remain with the error will equal to remain with xy minus xc ey then plus 1 ex. This one here we have approximately to 0 that term over this one here approximately to y squared then minus x over y. If we create a common denominator, the LCM here will be y squared. That means that's y squared. So when you divide y squared, you will have 1. So our error will be xy minus xey plus y ex. Then when you divide y squared divided by this, you will have y goes up y squared divided by y, remaining with y dividing here. So when you get the y times the x, you have minus xy. Minus xy. So this term and this term they are the same, they will vanish. Then we remain with the error will equal to negative x ey plus y ex then over y squared. And since you're interested in the absolute error, the absolute error, we introduce the magnitudes on both sides. So this one here will be negative x ey plus y ex over y squared. So this y squared, even if you put it in the magnitude form, you don't put it in there because it is a square. The whole purpose of putting in the magnitude is to eliminate the negative sign. But in a y, even if y is the negative value here, for example, if y is negative 4, in this term here, the y squared will always be positive. So even if you don't put it in the bracket, you always put it there or you don't put it there, it is all the same. Because the whole purpose of introducing the magnitude is to eliminate the negative sign. So, when you are separating here, when you are separating at this stage, don't forget to use the linear, the triangular inequality principle. You say that this relation can be less or equal to negative xey plus y ex and everything is over y squared. So this x goes with its negative. But the moment you introduce the magnitude here, this one becomes positive. So you have, now you can write that this is x magnitude of ey plus y magnitude of the error in x and everything is over y squared. And that is the absolute error, which is committed in the product of two numbers, the quotient of two numbers. So we look at the relative error. The relative error in the product, the formula which you can use. So this is a quotable result. If they give you the numbers, you can quote direct. Say x times the error in y plus y over times the error in x over y squared. Then you get the absolute error in the quotients. Then, if you want to say that the relative error is equal to absolute error over the inexact value. Over the inexact value. And the inexact value, it is the x, consider the x over y. The inexact value, when we go back to the system here, this is the inexact value, the working value. This is the small x over small y. That is the inexact value. So when we go back to the system of getting the relative error here, we shall have it as this is the absolute error, which is the ey plus the y ex then over y squared. Then you are dividing it with, so we are dividing here, dividing y over x over y. So it changes to y over x when we are dividing. Here, the absolute error is this term, and we're dividing it with the x over y. So it reverses, then the y goes up, and this one comes down. That's when we divide this whole term. Because the inexact value here, it is the x over y. By principle of mathematics, this one here will go up, then this one will bend down. That is when dividing x over y. So it becomes this. So this y will reduce this y here. Then you make the relative error equals to x magnitude of ey plus y magnitude of ex. Then everything is over this x is multiplied. Remember this same power has gone with that one, so you make it x y. So the relative error becomes the x into ey over xy plus this one here, which is y, ex over xy. And this x vanishes with this y vanishes with that. Then you make the relative error is equal to magnitude of ey over y plus the magnitude of ex over x, and that's why we obtain the error, the relative error. I will give you the quotient of two numbers and I want you to get the relative error. You can put it direct, the ey over y plus x over x, then you get the relative error without going through the series of getting the maximum value and the minimum value. But the choice is yours. You can use to import the formula, and you just substitute the values, or you can use the maximum and the minimum values. But many times you find when it's required you to show that the relative error is given by this, you show that the absolute error is given by this, and when you are deriving this step is very important. When you skip out to make this assumption, the whole process will become invariant, because if you eliminate this one and this with the ex and the ey squared, you have eliminated, you have to first make this assumption, assume that they are very, very small, so that you can eliminate them at the next stage. So that is how you generate a general formula which can be used to get the absolute error and the relative error and the percentage error for quotient of two numbers.